Welcome back. In this video, we're going to continue learning about net ionic equations, as well as the driving force that allows chemistry to occur. We're going to be focusing on the formation of weak and non-electrolytes and the formations of a gas as the driving forces of the chemical reactions. In previous videos, we looked at the formation of a precipitate, and in the future, we'll look at redox reactions. So an acid-base reaction or a neutralization reaction involves adding an acid and a base, and they form salt and water. For this reaction, we can have the formation of a weak or non-electrolyte as our driving force. Water is a non-electrolyte, and so its formation will be the driving force of the reaction and is therefore part of the net ionic equation. When writing out acid-base or neutralization reactions, you first want to write out the balanced molecular equation. So let's say we've got hydrochloric acid interacting with sodium hydroxide. The products of this would be a salt, in this case it's table salt, sodium chloride, and water, H2O. Notice that in this case, the water is a liquid. In acid-base or neutralization reactions, water is always formed as a liquid. Then we can dissociate any soluble, strong electrolytes to write out the complete ionic equation. Remember, solids, liquids, and gases are non-electrolytes. For aqueous solutions, you need to identify whether or not the compound is a strong electrolyte. So that's going to include our strong acids, our strong bases, and then any ionic compounds. So hydrochloric acid is a strong acid, so it's fully dissociated. Sodium hydroxide is both ionic and a strong base, so it's fully dissociated. Sodium chloride is an ionic compound, and therefore it's fully dissociated. And then water is written out as H2O as a liquid. Now, we identify the spectator ions. And these, again, are the ions that appear on both sides of the equation. So we have chloride, which is both aqueous on both sides of the equation, and sodium ions, which are the same on both sides of the equation. That leaves us with our net ionic equation, which is hydrogen ions plus hydroxide to react to form water. And this is the net ionic equation for all strong acid-base neutralizations. I'm going to now walk you through an example where we have a weak acid or a weak base and show you that the net ionic equation in that case is different. So this is still a neutralization reaction because we're reacting an acid with a base, but we end up with a different net ionic equation. Let's write out a balanced molecular equation for the reaction of hydrofluoric acid, which is a weak acid, and sodium hydroxide, which is a strong base. This would form sodium fluoride, which is an aqueous salt, and then water. We will dissociate any soluble strong electrolytes and write out the complete ionic equation. And so in order to be able to do this, you need to know your list of strong acids and strong bases. You might be tempted to dissociate hydrofluoric acid into H+ and F- because it's an acid. However, because it's a weak acid, the vast majority of the hydrofluoric acid molecules stay together, and so they don't dissociate. Sodium hydroxide is a strong acid. Sodium fluoride is a salt, and so it dissociates. And then we have water. Now, when we write out the full ionic equation and identify the spectator ions, we notice that this is a little bit different from what we saw before. Before we had H+ and OH- and then the rest of the salt. However, we only have sodium ion as a spectator ion. The fluoride is not a spectator because it's changing from being as part of the hydrofluoric acid to the lone fluoride ion. Because of this, because hydrofluoric acid is a weak acid, then the fluoride gets included as part of the net ionic equation. And so we'll notice that for weak acids or weak bases, our net ionic equation will look different than for a strong acid and a strong base. The final driving force we're going to talk about today is the formation of a gas. So this could produce any number of gases, but it could include carbon dioxide, hydrogen sulfide, nitrogen, sulfur dioxide. It's going to be a little bit harder to predict on your end whether or not some substances will form a gas as a product, but as you practice this, it becomes easy to identify. Another way that we could form a gas is through producing a molecule that decomposes in order to form a gas. So for example, carbonic acid can decompose into carbon dioxide and water. Here's an example. If you've ever taken baking soda and vinegar, then you know when you add them together, you get lots of bubbles. The reason for this is because it's forming a gas. It's forming carbon dioxide, which is driving the reaction forward. So the balanced molecular equation is sodium bicarbonate with acetic acid. This forms carbonic acid, H2CO3, and sodium acetate. As I mentioned earlier, carbonic acid can decompose into carbon dioxide and water. So our full balanced molecular equation is sodium bicarbonate reacting with acetic acid to form carbon dioxide, water, and sodium acetate. For our complete ionic equation, or sometimes called the full ionic equation, we need to dissociate any strong electrolytes which are water soluble. Sodium and the bicarbonate are an ionic pair. Since they're aqueous and the bond there is ionic, they fully dissociate. However, bicarbonate is not on your list of strong acids, and therefore it does not fully dissociate. Neither is acetic acid. It's a weak acid, and therefore it stays in its molecular form. Any gases or liquids that are produced stay in their molecular forms. And then finally, our sodium acetate is a strong electrolyte because we have a pairing of a metal with a group of nonmetals that are aqueous. So we can eliminate the sodium ions, and that leaves our net ionic equation being the bicarbonate ion interacting with acetic acid to form carbon dioxide, water, and acetate ion. That's it for this video. Thanks for watching. Have a great day.